Okay, so we've looked at the first law of thermodynamics, that heat cannot be created or destroyed. But for the second law, we're going to talk about the fact that what happens is that heat, it flows from a hot object to a cold object, never from a cold object to a hot object. And that's actually just a probability, but it's a pretty high probability. So a couple of examples here, you can rub your hands together and make it warmer. So you can easily convert work into heat, but you can't convert 100% of the heat back into work. So another example here is a car. You fill up the gasoline tank. About 25% of it is going to go into moving the car. 75% of that energy is wasted to heat that cannot be returned, at least not 100% of it, to usable energy. Work has to go into converting any of it. We're going to look at Carnot's principle as far as a heat engine goes at the end here, but let's talk about what's happening. The principle says that you can only convert all heat in a reversible process. However, spontaneous processes aren't spontaneously reversible. So we have to put work in to reverse something. So we would have to put work into getting that heat back into usable energy, back into gasoline, for instance. So spontaneous processes like the glass shattering when dropped, they don't spontaneously go back and form themselves into glass. And this has practical applications for heat engines. You can't get all the work from the heat added. So a couple of things with this is that you hold open the refrigerator if it's hot. I guess most people have air conditioning now, but back in the day, open up a refrigerator to cool off. You're really only heating up the kitchen. And an air conditioner unit has to have the sink, what's called the heat sink, on the outside of the house. Otherwise, it would only heat up the room. So basically, useful energy is lost to heat that cannot be reorganized and used again, at least not 100%. Therefore, the second law could also be stated that natural systems tend to proceed toward a greater state of disorder. Unless work is put into the system, it's not going to reorganize. So the entropy of the universe increases in all natural processes. So we'll talk about that a little bit more. So talking about entropy a little bit more before we go back to the heat engines. There's this order is called entropy. And entropy is a measurement of that disorder. And another way to look at it is positional probability. The more places something can be, the more entropy or disorder there is. And so you can think about different things that happen if we melt an ice cube. We put heat into a system. The molecules are going to be moving around more. There are more places for it to be. The entropy is going to increase. Entropy, the sign for entropy is positive if it's increasing for the system and negative if it's decreasing. There is a relationship here between entropy and heat flow and temperature. For instance, that's in another slide here. If we go back here, the entropy here, I've got a heat flow, and heat flow is going to increase the entropy, although the temperature of the system also comes into play, and we'll look at that in the next slide. The biggest thing to take away about entropy is that the universe's entropy increases in spontaneous processes. But also the thing you need to keep in mind is that the universe is made up of system and surroundings. So the system's entropy could decrease, but it'd be at the expense of the surroundings' entropy. So arguments have been made, well, living organisms decrease in entropy. You take all these random things and you make something very complex and organized. And that's true. So the system's entropy could definitely decrease, but it's at the expense of the surroundings, because in any spontaneous process, the entropy of the universe will increase. Exothermic reactions are preferred by nature because it gives up heat and increases random motion, thus increasing entropy. However, like we mentioned before, with S, the change in entropy being equal to Q, heat flow over temperature, it's going to depend on the temperature. So this heat flow that comes into a system may raise the entropy a lot, but it also depends on the temperature. So if the temperature is huge, a little bit of this isn't going to make a huge deal. So that's my example here. Bill Gates, if you gave Bill Gates $100, you'd feel considerably poor about Bill Gates wouldn't really care so much. So just to kind of recap here before we go into the heat engine, the first law of thermodynamics is a universal law with no exceptions. But the second law is really probability. It's just that our probabilities always seem to happen. It's a really high probability, but it is just a probability. And the third law can be stated, just like the second law, a variety of ways, but comes down to the entropy increase of the universe. The entropy of a perfect crystal at 0 Kelvin is 0, and beyond that, everything has disorder. A diamond actually comes close to 0 entropy, around 3 joules per kilomole. So some interesting things that have been talked about with the 3 laws is the first law is you can't win because you can't get any more energy out of the system than you put in. The second law is you can't even break even because you can't even get out as much energy as you put in. We'll look at that calculation. And the third law is you can't get out of the game. The entropy of the universe is always increasing. Some things to kind of think about here. Ralph Waldo Emerson, when this was first being talked about as a scientific principle, argued that human thought grows increasingly refined and organized through time. So it just proves thermodynamic laws. But, oh, those poets. But scientists tell us that the entropy of the universe is continually increasing. And the thought is, was there ever a point of perfect order if we go back in time? Because entropy is thought of as time's arrow. And there are some interesting articles out there in reversing time's arrow and that kind of thing you might want to look up. Okay, so the state of things thermodynamically is that ultimately there'll be a heat death of the universe, but that's going to be a while from now. That the entropy of the universe reaches a maximum value, which everything is in thermal equilibrium, and the temperature is uniform throughout the universe. And if there are no temperature differences, then that transfer of energy, work will be impossible, and a state of perfect disorder will exist. Okay, so back to some realistic calculations here with Carnot's principle. Heat engines are cyclical. Entropy increases in any spontaneous process, but if it's a cyclical process, it has to reverse at some point to go back to the starting point. And spontaneous processes are not spontaneously reversible, so work has to be put in to reverse it and decrease the entropy. So if work has to be put into the cyclical process, then not all work can come out at 100% efficiency. So that's a basic idea behind it. We have a formula here that we can calculate the efficiency. And the bigger the difference between the added heat, which is sometimes called the hot reservoir, and the cold reservoir, which is the heat that's being removed, the bigger the difference here, the more efficient it's going to be. Okay, so our formula here, we're going to be using that. If you look at a very typical heat engine that occurs, we have heat added through combustion of some sort of fuel is burning. And notice here that this is a constant pressure, but the volume is expanding. So going back to our last video here, if it's a constant pressure and the volume is expanding, the only way that that's going to happen is if we put heat into the system. We have an output of work run to the compressor, and this useful work is available to move a piston. And then there's a cold reservoir here, and the heat is exhausted, and again you see a compression of the volume at a constant pressure. And if that's going to happen, we better get rid of some of that temperature, because remember, from like an airplane cabin that is compressed, the air is compressed, and the heat would be unbearable if we didn't remove it. So same kind of idea, and then it goes back through the cyclical process. So the efficiency here, let's just do a couple of problems. The efficiency of an engine that receives, so this is the energy coming in, added, and this is the energy that's being lost here. So to do that, we're going to say the efficiency is going to be 1 minus the loss kilojoules over what has been added, and we can calculate 0.15 or 15% efficient. So, not great. All right, let's take a look at this one. We have an engine is 21% efficient and loses 780 joules to the cooling system. So this is the Q removed, and this is the efficiency, the 21%, like this was 15%. And so I'm going to say 21% or 0.21 is going to be minus, and this is going to be the loss, and we don't know what is added. So be careful with your algebra here. Remember, algebra can be a little bit tricky. So what's going to happen here is I'm going to go 780 over that Q equals 1 minus 0.21. And then I'm going to go Q added is equal to 780 over 1 minus 0.21. So just be a little bit careful there. And you get 987 joules. So that's not the final answer because they're looking for work. And the net work is going to be, well, what did I add versus what did I do? So Q added minus Q lost. And we just got that Q lost, or we said the 780 is what's Q is lost. So 780 goes down here, and the 987 goes here. So 987 minus that 780, we get 207 joules of work. That was